So good afternoon, everybody, and welcome to this week's Heidelberg Joint Astronomical Colloquium. And I'm very happy to welcome today's speaker, Myriam Benisty of the Institute for Planetary Sciences and Astrophysics in Grenoble, who's making a virtual return to Heidelberg to tell us about some exciting new observations of distant planetary systems. So I'd like to call on Myriam's host, Kees Dullemont, to make the formal introduction.
Yes, so thanks, Richard. So yes, it's a great pleasure to have Myriam here in Heidelberg, though virtually it would have been, of course, not even nicer to have her in real life here as was originally planned. But no need to be all that sad because she will actually come here in April, I think in the week from April 4 to 8, I think, right?
Yeah, exactly.
So then we will have the occasion to actually speak to her in person. But today she's here for the Heidelberg Joint Astronomical Colloquium and we'll talk about unveiling the early stages of planet formation. Let me briefly tell something about her. I guess most of you know her. She's well known for her observations of protoplanetary disks at a variety of wavelengths and scales, having worked on near-infrared interferometry during her PhD in Grenoble, and but since then also worked on observations at the near-infrared and optical with the VLT sphere instrument. So a number of famous objects have been imaged and interpreted by her. Famous pictures from HD 100453, HD 135344b, and MWC 480, which show these beautiful m=2 spirals. And right, so she's done her PhD, as I said, in Grenoble, working on near-infrared interferometry, then did a postdoc in Arcetri in Italy with Antonella Natta, then came here in Heidelberg for a postdoc at the MPIA, and then she got a permanent staff position in Grenoble, then actually relatively soon afterward went for a sabbatical in Chile, which took a little bit longer than originally planned, I guess, due to the Corona crisis. But she's back in Europe and got an ESC consolidator grant, which she's essentially now starting, sort of partially in Grenoble, but in effect, actually more in Nice at the observatory there. And so she's starting there and she's building up the group. And yeah, I guess many of you know that she's also done this famous work on the circumplanetary disk around one of the two planets seen in the PDS-70 object. So yeah, she has done a lot of these exciting things, and I guess that we're all looking forward to hearing about this and other stuff. But before actually giving her the word, let me just tell you why what I personally really appreciate about her, because she likes not only to do the observations, but she really wants to understand what the observations mean and what they tell us. And that means she actually loves to work with people who do models and do the theory, and work with students and inspire them to get the best out of their data, but also to get the best out of themselves. And so it's been for me always a great pleasure to collaborate with her, and I'm now very curious to hear what she has to say to us. So please, Myriam, go ahead.
Thank you very much, Kees. I've never given a talk after such an introduction, so I feel completely yeah, moved by what you said. Thank you very much. So yeah, I will present observational results on the early stages of planet formation. And as Case said, I like to understand what the observations say, but it doesn't mean that I understand everything. So I'll present very complex observations. These works have been done in collaboration with a large team, and really, I would like to acknowledge the work of PhD students who, which names are in blue here, or former PhD students. So Case already gave the outline of my talk. First I will, and I was impressed that you remember all the names of the targets, I must say. So I will first present why we care about getting such observations of the early stages of planet formation. And what in practice we've been living in the past few years, which is a revolution in terms of how we picture protoplanetary disks. We used to think of them as a smooth structure, and now we realize that they are highly structured. I would also like to focus on the fact that when we observe at different wavelengths, we can bring a lot of synergy between different techniques, which help us to understand what is happening in these objects. And I will finish the talk by focus on the so far unique system of embedded young, still forming planets embedded in their host disk. So the starting point is really this plot. So these are the population of detected exoplanets, the planet mass plotted against their separation from the host star. And we can see already from there that there is really a broad diversity in the exoplanetary system, both in the nature of the planets. So we have really giant planets and terrestrial mass planets. But we also have a very broad diversity in the architecture of planetary systems. So depending on the techniques, you are obviously sensitive to a different kind of planets, but we have detected so far large separation, massive giant planets orbiting at tens of astronomical units from their star. And at the same time, we know that we have very compact system within one astronomical unit with multiple planets there. So the question there is, how do you get to this diversity? And are the initial conditions for planet formation responsible for this diversity? Can we understand this diversity from the physical and dynamical and chemical conditions that are at the time where the planets are forming? So this is the classical picture of planet formation, where you have a young stellar system that is evolving with time. And at this stage of about 1 to 10 million years, the young star is surrounded by an accretion disk made of gas and dust that orbits the star. And at this stage, we think that planets are being formed. So we used to call this a circumstellar disk, but now these days we call it protoplanetary disk, and even more recently started to call them planet-forming disk, assuming that planets are forming in this disk. But this is actually already a bit of a speculation, because we don't really know if planets are forming at this stage or actually earlier in the stellar evolution. So with time, the gas dissipates and planets are formed, and we end up with a planetary system. So in this talk, I will focus on this type of systems that are about 1 to 10 million years old. So how do we form planets? The first thing is that we need to grow a planetary core. And the first scenario is called the core accretion scenario, where we start with microscience, sub-microscience grains from the ISM that must coagulate and grow towards pebble sizes, meter sizes, and then kilometer-sized bodies. Then you have accretion of gas to form a giant planet. From the observational point of view, what we can observe so far are only this kind of dust grains. We're not sensitive to larger bodies. The other scenario is the fragmentation through gravitational instabilities. So if you have a protoplanetary disk that is cold and massive, then in the outer disk regions, there could be gravitational instabilities and then collapse of core that will form gas giants. So in principle, we have these big scenarios, but it's still unclear in terms of the population of exoplanets that we have observed until now. What is exactly the mechanism that is dominating? And also, obviously, all the details of these two scenarios. So it's still unclear how planets form, where exactly in the disk they form, the inner disk and the outer disk regions, and when exactly, at which state of the stellar evolution planets will form. What we also do not know is how do these planets interact with the disk. And for example, if you form a giant planet like Jupiter, it has a dramatic impact on the subsequent formation of lower mass planet. Like in our own solar system, Jupiter has had a dramatic influence on how the terrestrial mass planets could form. Then we think of planet formation as being the key focus of the studies on protoplanetary disks. But we know that the disk by itself evolves. So we have viscous evolution of the disk, we have disk winds, photoevaporation. So in principle, and a bunch of instabilities occurring in the gas. So while planets are forming, the disk itself is evolving and through a bunch of mechanisms. And these two aspects really act at the same time. So there is this constant feedback between planet formation and disk evolution. And it's unclear how planet formation is affected by some aspect of the disk evolution and the other way around. So as observers, what we want to do is really to constrain and understand the structure of the disk and their evolution at the time of planet formation. And I will have a focus in this talk on planets, but obviously there are many of the aspects that I will show that could be also interpreted without planets. So to go back to planet, what kind of signature does a planet forming in the disk have? So the first thing is that when you have a planet embedded in the disk, and this is a hydrodynamic simulation, the planet, a massive planet, will carve a gap. It will deplete a region around its orbit. And then it will also trigger spiral arms. So what we could try to observe are these two things, gaps and spirals. And a gap, a region of the disk that is depleted, has a direct signature in terms of observation. So this is a spectral energy distribution of a young star in gray. And in addition to the emission of the star, we have the emission due to the dust in the disk. And the continuous disk will lead to an excess in the infrared emission and at longer wavelengths. Now we have a planet in the disk that carves a gap. You will have a region that is depleted of material and depleted of dust. For example, here, a large empty cavity. And this will create a lack of emission in the infrared wavelengths that you can directly identify by just looking at the spectral energy distribution. Then you have a planet in the gap, and this has been a lot of work by Kay Still and Paola in Heidelberg. So you have a massive planet embedded in the disk. So this is, again, a hydrodynamic simulation. This is a 1 Jupiter mass planet. You will carve a gap. So the planet will carve a gap in the gas, but this has a direct impact on what we can observe through the dust. And why is that? It's because the dust grains will be coupled to the gas and will follow the gas motion. And depending on the grain size, the dust grain size, you will have different kind of coupling. And you expect different consequences in the dust distribution. And this shows, for example, the distribution of the dust grain sizes within such a gaseous disk. So you have here the radial profile of the gas density, basically. And in the colors are the different grain sizes. And what we see is that the large grains, so the large grains here, so the ones that are above 1 centimeter in sizes and millimeter, are actually trapped at the pressure maximum, so outside of the orbit of the planet, and that the amount of grain sizes, the amount of dust grains will grow at this area. The small grains, on the other hand, can actually be distributed over a much broader range of radii and can flow within the gap created by the planet. And then these are dust and gas simulations, but if you do the post-processing with relative transfer to predict how observation will look like, you see that depending on the wavelengths that you are looking at, you will have different predictions. And I will explain this in a minute. So the small grains are actually distributed within the orbit of the planet, and you would expect something like a full disk. On the other hand, the large grains that are trapped beyond the orbit of the planet will lead to a ring-like observation at the sub-millimeter wavelengths. So by looking at different grain sizes, at different traces of different grain sizes, you can directly infer the presence of a planet. Now, if you have a massive planet, for example, a disk that has a low viscosity, what you can get is actually multiple gaps. So I showed you an example with one gap, but one planet can actually lead to, for example, here in this case, 3 gaps. And that leads also to 3, for example, rings. So we can observe multiple rings due to a planet. And if you have a massive planet, or here in this case, 2 massive planets, what you can also get is instabilities at the edge of the gap created by the planet. And these are these 2 areas here that will lead to asymmetries in the observations. And the final kind of structure that a planet can carve and can lead in a protoplanetary disk is misalignment. So if you have a planet, a massive planet, say 10 Jupiter mass planet, that is embedded in the disk, as we saw before, it will carve a gap and then generate spiral arm. But in this case, the planet is actually inclined with respect to the disk. And that is motivated by the fact that we have observed planetary systems where planets are actually misaligned with respect to the plane of the disk. And in that case, if you have a misaligned planet, what you can see here is that it will tilt the inner regions of the disk and tilt it along its orbit. And what that will do is that you will have some regions of the disk that are misaligned with respect to the outer disk regions. And that has a direct implication of what we can observe. And why is that? Is because if you have a star here and a misaligned inner disk, you would irradiate the outer disk regions differently. In that direction, you would irradiate the inner regions of the disk, and then you cannot irradiate anymore. This will be in the shadow of this inner disk. On the other side, you will irradiate the full disk area. So these misalignments are thought to generate shadows in our observations. So to summarize, we can look for evidence of planets through the structure in the disk, through the presence of rings and gaps, asymmetries, shadows, and spiral arms. So how do we do that in practice? We observe a disk and multiple wavelengths, and that is very powerful. First, because if you just think in terms of the energy that you will get, if you look at cold, just like a black body emission, if you look at cold layers, so the midplane of the disk, you can observe in the sub-millimeter. Now, if you want to look, observe in the infrared, you will be sensitive to very hot regions of the disk. So for example, the innermost disk regions that are at temperature of more than 1000 K. And by doing this at different wavelengths, we're observing different layers of the disk. But as we will see in a minute, you are also sensitive at to different dust grain sizes. And why is that? Is because we observe dust grains through their opacity. And these are plots that show the opacity of different population of dust grains versus the wavelengths. And the different lines correspond to different population with different size of grains. So for example, if you observe in the near infrared, you are very sensitive to small grains that have about the wavelengths or about the size of your wavelengths. If you observe in the millimeter regime, then you're very sensitive to the emission of grains that are at about pebbles, so 1 millimeter, 1 centimeter grains. And large grains tend to settle towards the midplane and are located around in the midplane, where small grains are lifted up through turbulence towards the surface layers and are more easily observable in the infrared. So in my view, the best way to study protoplanetary disk is to have a multi-wavelength approach. By doing that, you have access to different regions of the disk, different dust sizes, and then you can directly constrain the dynamical processes that are happening in the disk. For example, if you observe in the sub-millimeter with ALMA, you're sensitive to the midplane, cold layer, and you're directly probing the bulk of the mass of the disk. So you can get access to the density and temperature of the observation with a resolution of about 5 to 10 astronomical units. If you observe in the infrared using an 8 to 10 meter class telescope, you're sensitive mostly to the scattered light. So the stellar light that is scattered off the small dust in the surface layer. So you're sensitive really to the shape, the overall shape of your disk. And right now we have a resolution of about 5 astronomical units. We have to mask the central star because it's too bright. So we use a coronagraphic mask, which prevents us from looking what is inward of 10 astronomical units. To look at what is within few astronomical units, you need to use near-infrared interferometry like the VLTI. You can get down to 0.3 astronomical unit resolution, and you're really probing the micron-sized dust grains also in the surface layer within 1 AU. You can complement this obviously with tracer of the gas to have a complete picture of the dynamics of dust and gas in your disk. So now I'll present an overview of the observation that we have been obtaining at these wavelengths in the past few years. So as soon as we had access to long baseline observation with ALMA, we realized that the protoplanetary disks in general are highly structured. We see substructures in basically any bright and extended disk. And the structures that we see are the one that I presented that we are expecting from planet disk interactions, namely concentric rings and gaps, spiral arms, and asymmetries. And this is for the millimeter thermal emission of the dust. And you can see that these asymmetries could be coming with other kind of structure like rings or isolated in the image. So far, we have observed about 120 disks with a resolution of 10 to 20 AU. And here I show the disk brightness against the stellar mass, and here the disk sizes against the stellar mass. That's the work by time long. And what we found is that disks that show substructures are about 60% of these disks are very bright, and they're also the largest one. Now, if we look at the disks that do not show substructures at this resolution, they could still be bright, but what we find is that they're very compact. And that tends to tell us that we have still a limitation in how much we can resolve these substructures. Indeed, if we look at the subsample of these disks that have been observed with a high resolution of 10 astronomical units, we find that this frequency is higher. More of these disks show substructures. And that tends to tell us that basically we need to push further the angular resolution of observation to have a complete view of the substructures in these disks. The rings and the gap are the ones that we find everywhere and around all kinds of disks, young and old, and different around different stars. What we found, and this is the radial profile, for example, of an image of one disk, is that the rings and the gap have different contrast throughout the disk, but also within different objects. We also find these kind of asymmetries, as I was showing before, mostly around massive young stars, intermediate mass young stars. And the spirals that we form in the millimeter are rare, but are seen both around multiple stars and single stars. And I'll explain in a minute why this is important. Now, if we move to shorter wavelengths, the infrared, we have the same conclusion, basically that we find structures in all kinds of disks as long as they are quite bright and quite extended. So you can see here a variety of substructures. But basically, we have three main categories. Again, the accumulation of rings and gap, spirals, and what we call shadows. But we have to keep in mind that what we observe is really that we have one region of the disk that is darker than the other region. So we are actually interpreting what we're seeing as being due to a shadow, due to a misaligned region in the disk. So all of this structure could be tracing planets. In general, in the infrared, we have observed about 130 disks with an angular resolution of about 10 AU. And about half of the ones that we detected have substructures. But in the infrared, one aspect is quite tricky, is that some of the disks, for example, this one, appear to be very compact in scattered light or very faint. And we could think that this means that the disk itself is very compact, but in the sub-millimeter, we find that this disk is actually very bright and very extended, this one here. So what happens here is that this disk is self-shadowed. So we have the inner disk regions that are puffed up due to their thermal structure and cast a shadow on the outer disk region. So basically this disk cannot be detected. What we found when we look at the demographic of these substructures is that, for example, the rings, so here in blue, are associated with targets that have a low near-Infrared excess in the spectral energy distribution, while the spirals are actually associated with targets that have high near-Infrared excess. And what does this mean? The near-Infrared excess is a way to trace the amount of reprocessing that we have in the innermost disk regions that we cannot access with these techniques. What we found is that the targets that have spirals are the ones that have a lot of dust lifted up, very high up at high altitude in the inner disk region. And that's another way to think that there might be a very massive perturber in the inner disk region, really perturbing the disk and lifting up all of this dust. Now, as I said before, there are other possibilities than planets and companions to explain all of these substructures. And there is a lot of theoretical models, including those that do not invoke planets, such as stabilities that could lead to rings, for example, and spirals. What, as an observer, I can say is that the models are great, but they have a lot of assumptions. For example, how they treat the thermodynamics, or whether it's 3D or 2D, that will have a significant impact on the predicted substructures of these models and on the way we can interpret them. So this is still, in general, a very active field of research. So what can we learn with these substructures? First, if we go back to rings and gap seen in the submillimeter that we think are the most common, as I was explaining before, these are potential evidence for the fact that grains are trapped in the narrow regions of the disk. And why is this important? Because to be able to go from micron-sized dust grains to planetesimal, we have to have very favorable conditions for these grains to grow. And these traps are natural region for them to grow. And this is the work of K. Stilleman on what we call the D-sharp sample of disks, where he looked at whether these rings that we see, for example, in this case here, are natural traps where grains could grow. And a very nice way to check this is to look at the width of the ring. If the width of the ring is smaller than the pressure scale height of the disk, so the typical scale of the disk in the gas, then this is a strong indication that there could be dust traps. And this is the case, for example, in this object for this second ring here, ring 2. And the fact that the optical depths that we measure in these rings is nearly constant could be an indication for the fact that these are regions where actually grains grow to planetesimal that we cannot observe through our wavelengths. Now, another indication for the potential dust growth in these traps can be obtained by looking at these rings at multiple wavelengths. If you look at multiple wavelengths, you can constrain the slope of the opacity of the dust. And that tells you a constraint about the maximum grain size that you have there. So in that case, still the same objects, rings were observed at 2 wavelengths, at 3 millimeter and at 1 millimeter. And by modeling this observation with relative transfer and including population of dust grains and dust size distribution, Aníbal Sierra was able to basically predict the surface density in the dust radially. So you can see here the inner disk and here the 2 rings, and found that it's actually only in the second ring that there is evidence for larger grains than in the first ring. So this is consistent with the previous slide. Now, if we move to rings and gap but seen in the infrared, as I was mentioning before, in the infrared scatter dye, we're really sensitive at the surface layers. So what can we do with these rings and gap besides inferring the presence of planets? What we find here, for example, in these disks, there are multiple rings. Here you only see half of it, but there's one here and one here, and then another arc here. What you can notice here is that these rings are offset. They do not share the same center. And this apparent offset is actually tracing the surface shape of the disk. And indeed, in multiple objects where we observe these rings, we can infer the global shape of the scattering surface, which we can then relate to the shape of the gas surface and then relate to the thermal structure of the disk. Now, spiral arms, what can they tell us? First, where do we see them? We see them in general in disks that have cavities, so dust-depleted cavities. The one that we think are single stars, around single star, we call them transition disks, and otherwise they are circumbinary or multiple disks. For example, in this case here, we have a dust-depleted cavity. The gray mask is just the chronographic mask to hide the star. And we see that we have a ring and then these two spirals. On the right side here, these are multiple systems. So we have here a binary star, and here you can see that we have multiple spirals that do not exactly resemble the shape of these spirals here. This one here is a famous object, GG Tau, where we actually have a quadrupole system here. And you can see that in addition to having multiple spirals, we have also shadows and a lot of filaments here, so very complex structure. So we can, in principle, use the morphology of these spirals to estimate the planet mass or the companion mass, for example, that is carving the cavity here and responsible for the spirals. We can also infer the thermal structure of the disk by using, for example, the opening angle of these spirals. But this is quite challenging. Now, in the sub-millimeter, spiral arms are much more rare, but there is one beautiful case, which is the one of this disk, LIS-27, where we saw these spirals in the sub-millimeter continuum, so sort of like implying that these spirals can trap the dust grains. And what we found in this disk, in addition, is that when we look at the intensity of the gas, that one side of the disk is more extended than the other side. And that we inferred that this could be due to two different heights of the disk, depending basically on whether it's on the east or on the west, so a highly perturbed disk. And if we look at the channel maps or the velocity maps of the emission of the gas, what we found is that they are clear non-Keplerian features collocated with the spirals. So we expect that in a smooth disk, the gas rotated Keplerian rotation, but in this case, we see very strong non-Keplerian motions. And this is actually consistent with what we expect from gravitational instability. So this might be so far the unique case that we have, where we think that we are actually witnessing gravitational instabilities occurring in this disk, which could lead to the formation of a planet or planets. Now, another kind of feature that I mentioned before is shadows. So the shadows tell us about the misalignment of different disk regions. And this is the object that Case was mentioning in the beginning of the talk. And what you can see here is that we have a ring and dust-depleted cavities, what we call the transition disk, two spirals, and associated with the spiral, these two dark regions. And we could reproduce this observation with a relative transfer model under the conditions that we would have an inner disk that is highly misaligned with respect to the outer disk. So we built this model by considering an outer disk that has an inclination and position angle that matches, the observation here, the ring. But for the inner disk, we use a constraint from near-infrared interferometry to have the inclination and position angle. But if we consider this with just this number, we couldn't get the shadows right. To get the shadow right, we had to flip the inner disk, basically, and have the near side of the outer disk be that one, while the near side of the inner disk is this one, the one that is the side that is nearer to the observer. So in general, if you have an inner disk and you misalign it only of a few degrees, you get a very broad shadow on the outer disk. And then if you misalign it more, you get a very narrow shadow as the one that we observe here. And that case is another kind of observation on another object for which we actually have an east-west shadow. And in that case, we actually interpret it as being due to a mild misalignment of about 30 degrees. But what we found is that in some cases, these shadows are actually dynamic. They change with time. So these are observations of the same disk as I showed before, where we have 1, 2, 3 shadows. And you can see that the aspect of the disk changes with time. And it's even more striking in this case here, that was published by Paola Pinilla, where we have a ring of a transition disk and 2 shadows here. And you can see that the 2 shadows changes the location and also the contrast with the disk with time. And if you pay attention to the time scale of variation, we found that this variation was were observed within timescale of a day, which is extremely short. So what we infer for this disk, that we have an inner disk that is almost polar, perpendicular to the outer disk. And that this disk, so to cast the two shadows here, but that in addition to this misalignment, we must have a very clumpy inner disk to be able to reproduce the movements of the shadow. And this inner disk must be really like stuck to the star. It's extremely close to the star to be able to reproduce this very fast time scale. Now I'll show a few examples that show what we can learn from the synergy between multiple wavelengths. And this is quite obvious just by looking at the disks. These are observations of the same disk. I am loopy, and here of this object here. When we observe them in the infrared scattered light, so really tracing the surface layer, and when we observe them in the sun-meter continuum, tracing the midplane. And what you can see is that these observations traces are looking at this, are tracing the same disk, but clearly the images are very different. So the main question here is, can we explain the structure in the surface and in the midplane with the same kind of mechanism? For example, if you think of a planet, is the planet responsible for both the surface and the midplane structures? And if that's the case, what can we learn in terms of the physics of the disk and in general the conditions, the physical and thermal conditions in the disk to reproduce these observations? And the first thing that we can learn is the dust dynamics. And this is these are beautiful examples that tell us, for example, that dust grains, large dust grains, settle towards the midplane, which is great because we need them to do that to form planets. So in these are these that I've seen edge on. So the colors show the Hubble Space Telescope's observation of edge on disks. So there are a few of them here, where you can see that we're tracing the scattered light due to small grains in the surface layer, so really high in altitude. The contour, the white contours here show the millimeter ALMA observation of large grains, and you can see that they are really concentrated towards the midplane of the disk. When we observe this disk at multiple wavelengths, also in the millimeter, so going from 0.8 to 2 millimeter, what we find is that we are tracing at longer wavelengths a disk that is even thinner and even smaller in radius. And that's consistent with the fact that dust grains settle to the midplane and also drift radially due to their interaction with their coupling to the gas. And in general, what we find with the study is that the overall level of turbulences in the disk is quite low, and this can be a very important input in the models of planet-disk interactions. Another thing that we can do when looking at different wavelengths is tracing, this time not vertically, but radially the motion of dust. And this is the same disk, TW Hydra, observed in the infrared and in the sun millimeter. This is the work by Roy van Boekel. And what we found is that in the two different wavelengths, not only the size of the disk is different, it's so much more compact in the millimeter, but also the location of the gaps, their width, their depth differs. And this is something that we expect also from planet-disk interaction, as I was explaining in the introduction. When we have a planet in a disk, we expect that the large grains are trapped at the pressure maximum, so much beyond the orbit of the planet. But the small grains are very well coupled to the gas, and the gas can still float inward of the planet's orbits towards the star. And the small grains that are well coupled will follow the gas and will be distributed inward of this pressure maximum. So we do expect to have this segregation in dust sizes. Now, the combination of ALMA and shorter wavelengths is also very powerful to look at, in general, the environmental effects that might affect planet formation. And for example, in this case, Auriga, we observed with the SPHERE instrument a beautiful image. We obtained a beautiful image where we can see a large tail towards the west, and also multiple spirals. And here you can see that we have this dark lane that is probably tracing a misaligned inner disk. And when we combine this observation with gas observation from ALMA, here are the red shifted velocity channel, and here the blue shifted emission, what we can see is that actually this emission and this tail in general might be tracing infalling material towards the disk. And this could be due to a late infall through a remnant envelope that will then trigger the spiral arms, but also a misalignment of the inner disk due to the angular momentum conservation. And this is quite consistent with simulated observations by case. So this could be responsible for a misalignment in the disk, but we thought that before misaligned planet could also be responsible for these misalignments. And in general, the question is, how often do we have misalignments in this disk? So to probe this, we search for misalignments in the innermost disk region by using the RTI, so the near-field interferometry. These are the kind of observations that we get, so visibilities that we then have to model with analytical models. So in that case of this object, this is our best model for the inner disk. So this is probing 0.5 astronomical unit. And we find an inclination and position angle. And we would like to compare the inner disk morphology to the outer disk morphology. For that, we use ALMA. And we use the gas velocity profile of this disk, from which we model with a Keplerian disk, for example, to infer the best inclination and position angle. We have a beautiful residual map that tells us a lot of things, but this is not the topic of this slide. So we have the morphology of the outer disk, we have the morphology of the inner disk, and we can compare them. And we find that indeed for this disk, we do infer a misalignment of about 70 degrees. So we looked at 20 disks, and at least 6 of them appear to be misaligned. And these are objects for which we have inferred the presence of shadows in the infrared scattered light. And using the inclination and position angle that we derive from the interferometry, we can actually predict the position of these shadows and find that they match pretty well the shadows observed in scattered light. The question now is it the inner disk or the outer disk that is misaligned? If you think of a planet, for example, the planet would basically tilt the inner disk, while a late accretion event could actually have an outer disk that is misaligned with respect to the star and the inner disk. And on a very, very small sample of 3 objects, what we find is that actually the inner disk is very well aligned with the stellar spin. So that tends to actually indicate that what we are seeing here is not the effect of a misaligned companion, but rather of a late accretion event. Now, I will focus the remaining time of the talk on the detection of embedded protoplanets. So if we think that we have all of these substructures, you can extract the population of planet that is in this disk, assuming a lot of things in your model. And we found that we have a lot of planets hidden there. But these planets are very difficult to detect with direct imaging because the planet is very faint and the disk is very bright. And these are the predictions for a bunch of disks. And in general, the planet masses that we could observe are still at the limit of a few Jupiter masses, while we might have lower mass planets generating these substructures. And in one of these cases, PDS70, we actually found 2 planets. So this is the detection of PDS70b at multiple wavelengths, multiple epochs. And that was then completed with the detection of PDS70c here in the H-alpha tracer. So we found them in the infrared and in the H-alpha, which traces the gas. These planets are quite massive, although their exact properties are still quite debated. We observed this system with ALMA, and we found that the large grains are trapped as expected in the ring, and these are the position of the 2 planets. And when we look at the object in the gas, this is an intensity map, what we can see that there is a gap that is carved in the gas emission. So that means that this planet, PDS70b, must be very massive. We see that there is some kind of a bridge connecting the outer disk to the inner disk through the orbits of PDS70c. We performed hydrodynamic simulation of the system. So we have these two planets here with PDS70c being less massive than PDS70b. And we let them evolve. And what we find is that the planets enter in a 2-to-1 mean motion resonance and with outward migration, very similar to our own Jupiter and Saturn planets. And these are the same simulation with dust grains there. And what we can see is that the large grains here in yellow are trapped in the ring, as expected, but that the small grains that can flow in towards the inner disk are also expected to be collocated with the planets. And in general, we found that there are accretion shocks because we observe the planets with H alpha. We expect to have them to have small grains around them. And in general, we think that planets are accreting through with the help of a circumplanetary disk. That basically we have gas coming from the disk, protoplanetary disk, accreting onto the planets through meridional flow and then readily expelled outwards. And so we searched for evidence of this circumplanetary disk with ALMA, and we found that we had an emission that was collocated with PDS70C. But we were not very sure because it was still connected with the outer disk. And then we looked at PDS70B, we had a 3 sigma blob here, but that was completely offset with respect to the position of the planet. So that was quite positive. So we reobserved this object with longer and higher resolution observation. And we found, we confirmed the presence of the circumplanetary emission collocated with PDS70C. So this is the press release image that is nicer than the contours plot that I'm going to show right now. So with this new observation, what we found is that we have this compact emission that is collocated with the planet C, and that is separated from the outer disk. So we interpret this emission as due to a circumplanetary disk. But to make sure it's a circumplanetary disk, we will need to actually probe the gas rotation around the planet, but that's beyond what we can do so far. We also detect a faint emission in the inner disk, meaning that the dust grains can still flow from the outer disk to the inner disk. And finally, what we found when we downgrade the angular resolution is that we have some faint emission around PDS70B, but of a very unclear morphology. From this observation, what we can detect basically is the flux of this circumplanetary disk, and we relate that flux to, assuming a couple of things like temperature, to the amount of dust grains that we have there. And so far, we can only have a lower limit for this dust mass because we have to assume we only have one wavelength, so we have to assume that the emission is optically thin. What we found in general is that the dust mass of the CPD over the planet mass is about 10 to the -5. The other thing that we found is that this emission is unresolved, and that sets a limit for how big the circumplanetary disk can be, about 1.2 AU. But it still emits a certain amount of flux, so it cannot be too small either. So that sets a lower limit of about the extent of the circumplanetary disk. And in general, we find that it's about 1 astronomical unit, which is consistent with what we expect from the theory. So in general, in this circumplanetary disk, what could be happening is that we have large grains that grow and form satellites in a similar way as we find planetesimal in protoplanetary disk. We confirmed the presence of this circumplanetary disk in using a model in the UV plane because ALMA provides us visibility. So we subtracted the outer disk to make sure that this was not an imaging artifact. And we modeled it with a very simple model. And find that indeed, the best model is for the emission here is very close to the planet C. But the emission around PDS70B is still offset with respect to the location of the planet. So this is a really puzzling results. And we don't really know if maybe the nature of these two circumplanetary disks are different, or if it's due to the fact that PDS70B is really within the orbit of PDS70C and therefore is starved of material. Finally, the final result is that this is not all, right? We still do not know whether these circumplanetary disks have large grains or or small grains. And it's the same for the inner disk. What we find is that the inner disk that is within the orbit of the two planets, so where terrestrial mass planets could be forming is very optically thin. So there is a very low amount of dust grain in the inner disk. We cannot be sure of the sizes of grain because we only have one wavelength, but we know that there is a very little amount of material in the inner disk. And what we found also in the outer disk, and this is a radial cut, is that the outer disk is actually not just a simple ring. It's a ring plus another feature within this ring. And that tells us that first there could be another planet sitting here, or that the structure of the outer disk and the planet disk interaction in general is highly complex and could influence what we see in terms of the circumplanetary disk. So to conclude, I hope I have showed you that in general, a multi-wavelengths approach is really key to understand the disk structure and how we can assess planet formation in disks. And in general, we have a bunch of features, rings, spirals, shadows that tell us about the possible presence of planet, but that we can also use to infer the physical conditions in the disks. In general, we have to compare to models, and models are improving thanks to observations, also because we challenge them in particular by taking into account the thermodynamics. In terms of observations, our surveys are still very biased towards the brightest objects, and there are still a lot of questions that remain. For example, what is the substructure's demographic in more compact disks, in disks around low mass stars? And how do these substructures evolve with time? And are they affected by disk evolution, or do they affect disk evolution? And in general, we usually observe these that are quite isolated. What is the impact of the environment on the substructures? And of course, what is the population, again, that is responsible for these substructures? And our goal is really to find them and try to characterize them. And for that, the future is really bright. We hope to detect more evidence for embedded planets through their impact on the disk structure using ALMA. So that's the goal of our large program, ExoALMA. Of course, James Webb will be key in directly imaging planets like Saturn mass planets, are really going lower in terms of the detection limits that we can get compared to the ground. And obviously, the perspective in terms of the use of the extremely large telescope are extremely exciting, because we will be able to probe the regions where terrestrial mass planets are forming and to detect them and characterize their properties. Thank you very much.
Thank you very much indeed. That is a remarkable tour of this very rich phenomenology. I mean, I must say, I'm taken completely aback with the details of the observations, and also impressed and taken aback by the details of the interpretations. It's certainly going to be something to look up going forward as you get even more interesting observations. I'm sure there's lots of questions going along in the minds of people, so please put your hands up. I see there's one. Yes, Jonas Kemmer.
Yes, thank you for this very nice talk. Maybe this is a naive question, and because I'm also very excited by all these structures that we see, but at which point do you actually decide that this should be a structure in the real image, or if it's an artifact from the reduction of the images? Because I think for sure, for example, and PDF 70, this is clear. We see this in different images, different wavelengths, etc. But for many disks, we have only one image or only one wavelength. How do you interpret this? And so my actual question would be, are there any structures that you see now more often in different disks that we cannot explain yet, or where we don't have any clue what it could be?
So to go back to the beginning of your question, indeed, I mean, so there are a few typical artifacts that we expect in an image that we can characterize well, I think. And then when we cannot characterize well the artifact, we in general repeat the observations. And that's, for example, what happened with PDF 70, right? We went back to the archive and find more observation of PDF 70 at different wavelengths. We try to confirm the results. That's the first point. For PDF 70, for example, with ALMA, we try to, because we observe visibilities and we do not have an image, right? So we reconstructed the visibility, we reconstructed the image in many flavors using many different parameters to make sure that this was not an artifact. And now, have we detected features that we have no clue about? Yes and no. I mean, there are basically a lot of these disks, and for example, the multi-wavelength challenge, where the same disk looks so different at different wavelengths. I don't think we have models that really explain both at the same time. So the answer is yes, or no, we cannot understand everything. On the other hand, we know that the ring could be explained by something, a planet, the asymmetry could be explained in another way. So we have hints to understand that.
Okay, yeah, thank you.
Okay, Ralph. Yes.
Thanks. That was a really fascinating overview of what we know about these disks and their environment. And as someone who works on star formation and is more interested in the ambient environment, it's really cool that we now have the tools at hand, or the first observations of how these protoplanetary disks are linked really to the star forming environment. So I was wondering whether these huge features you see are mostly caused really by, let's say, turbulence or structures in the blob of gas that formed the star and the planetary system, or could, to some degree at least, some of these misalignments, these features, be caused by dynamical processes? So not so much by gas dynamics, but by gravitational dynamics, tides in a dense cluster environment. So I was wondering, are the stars you have surveyed so far, the systems you have surveyed so far, mostly in isolated low density environments, or could it be that, you know, stellar encounters or things like that also cause many of these features?
Yes, indeed, we are very biased because we indeed try to observe these that are in quite isolated in general. But we find more and more evidence for dynamical interaction, for example, flybys. There are a lot of objects, not a lot, but maybe a handful, like 5 to 10, where we have very large scale streamers that usually we actually miss in observation because we zoom in, we run after angular resolution, so we try to zoom in, but we then forget about the large scale. And now we're going back to the large scale, and we're seeing a lot of these structures. And in general, for example, there's a Nature paper that came out, I think, a week ago on ZCMA, which is an outbursting FUR and her big BE binary, where there is a streamer that was connected to another star. And that indeed is clear evidence for this tidal interaction between stars. So it could be indeed that some of these structures are really due to that.
Okay, cool, thanks.
Okay, I think we've got time for 2 more questions. Roy van Berkel.
Hi, Myriam. Thanks a lot for this very nice talk again. I was fascinated by the result of the misaligned disks, where you find that the inner disks are aligned with the star and the outer disks are not, pointing at a late accretion event at a different angular momentum vector. And it made me think of many of these Herbig stars that are transition disks. They are big and very bright, but they are also typically rather old. And given what we know about the lifetimes of disks, they seem to be statistically a bit unlikely. Yeah, so I was wondering whether these could perhaps also be often, or maybe even generally, cases of these late accretion events. I was wondering what you think of that.
Yes, I mean, my conclusion of this slide was a bit provocative, I think, because one thing I'm not really sure is for example, if we have a misaligned, but basically, you know, the inner disk could at some point still realign with the star, even if it's originally not aligned with the star itself. So I'm not sure we can really conclude that these are late accretion events. I just found it interesting that for the 3 targets for which we have these measurements of inclination of the star as the stellar, the spin axis, it was in line with the inner disk. Now, whether it could be generalized to all transition disk Herbig stars, I don't know, because in general, they all have cavities, right? And we know that all of these disks that have cavities are just older than disk with no cavities, which means that whatever is in the cavity is, basically maintaining the stuff in the outer disk regions. But certainly it's an exciting result. I'm not sure what it means exactly, but it's interesting.
Thanks.
One more question in the formal part of the colloquium, I think. Paola.
Hi, Myriam. I just wonder, it's a general question about planet detections and CPDs. I mean, most of the models assume that planets are creating these cavities, but we just have PDS 70 found so far, so B and C. So what are your thoughts about it? Why we don't find more planets with a sphere and more CPDs with ALMA, even though there have been deep observations of several transitional disks?
Yes, so why don't we find more planets with sphere? It's very, very difficult because in general, the disk, so now we're looking at disks that have cavities of about a few tens of AU. This is usually the size of our chronograph. And then within this cavity, we are really limited because the disk itself is very bright. So to distinguish a faint planet from the disk signal is extremely challenging. So our detection limits are still a few Jupiter masses, but you could have multiple Saturn mass planets carving the same cavity, right? That's for what is inside the cavity. Outside of this disk, we could also have giant planets, right? But they might be of lower mass again. And that's why James Webb will be essential in assessing the kind of planets that we have in the outer disk. And I expect, actually, I'm hopeful that with the James Webb, we will find planets in, for example, gas gaps in the outer disk that we haven't found with sphere, because it's below our detection limit, but we be within the reach of James Webb. That's my hope. Now in CPDs, well, I don't know if we have so many super deep continuum observations in general, right? That's, for example, in gaps and rings, for example, it's tricky to have a good SNR for what is in the gap because you're also contaminated by the image reconstruction technique, I think. And then in cavities, yeah, it's a good question because it could be that these planets are lower mass, have a CPD that is not capable of retaining enough dust mass for us to see. That would be my guess.
Okay, thank you.
Okay, thanks. There's chance for more questions in our informal discussion, which will be just stay tuned after we finish the formal part. Before thanking Myriam, I'd like to make an announcement. I'll just take the screen. Oops. Yeah. About next week's colloquium, which will going on to the larger scales by Francesca Fracchiuti from ESO, who's going to talk about some various aspects of the dark content of Milky Way type galaxies in the context of observations and simulations. So now I think it's time to thank Myriam. So please open your screens and open your acoustic channel, and let's give Myriam a great send-off. Thank you, Myriam.